Hi, my name is Shaoshan Liu. I'm the CEO of Perceptin. In the past 10 years, my research has focused on autonomous machine computing, especially on autonomous driving and so on. Today, it's an honor to have an opportunity to make a presentation at ICCAD to discuss autonomous machine computing, especially the latest trend in the industry. So let's get started. So the topic of today's talk is vector graph acceleration for LiDAR-Inertial Odometry, which is a key utilization scenario in robotics and autonomous machines. The companion paper of this talk has been submitted to the conference as well as uploaded to an open source website. Welcome to check it out for more details if you are interested in this talk. And by the way, this talk focuses on the collaboration project between Tianjin University, Perceptin, as well as the University of Rochester from the United States. So what we have observed in the industry is there's a huge problem of talent gap, whereas a new domain like ours, autonomous machine computing, demand talents who understand both the algorithm side as well as the system side. The supply is extremely limited. And I think every company in this field today are facing a talent gap problem, as discussed in this paper titled Engineering Education in the Age of Autonomous Machines. And in the industry, we have been thinking what's the best way to address the talent supply shortage problem? How do we close the talent gap? And one way to close the talent gap is to have a very nice abstraction of the underlying system such that algorithm developers do not have to worry about system stuff, and system developers they can focus on optimizing a particular part of a system. So here is a concrete example of a level 4 autonomous vehicle. As you can see, the computation graph is a bit complex, even at a very high level. On the left side, you see a large amount of sensor data rushing in. And in the middle part, you see a lot of processing going on, one connected to another. For example, 2D perception gets input from camera, and then 3D perception gets input from LiDAR, and they fuse the data for perception fusion, then goes to tracking and so on. It's a very, very complex pipeline that we are dealing with today in the industry. One concrete example to facilitate or to implement the previous computation graph, at Perceptin, for example, we had to use multiple off-the-shelf compute components and connect them in a very nice way in order to implement the system shown previously. For example, in this work, which has been presented at Micro 2020, we show that we use the FPGA platform to handle most of the sensor processing. And then we send the data to the GPU for deep learning and CPU for planning control, and everything has been connected through a CAN bus. So it's very hard to come up with a system like that. And it demands, as I have mentioned earlier, it demands talent from the algorithm side as well as from the system side. And that's been a major challenge in the industry today. That's not the end of the story. If we just take one component, localization, and try to build a very nice system out of it, it takes a lot of work. For the first piece of work, which is presented in HPCA 2021, we show that it's very hard to build a generic engine to accelerate the localization function for robots, various kind of robots. And then a further improvement of that work, which has been presented in Micro 2021, it shows that to have a dynamic engine that can adapt to different environments, it's even more challenging. Again, it's a talent supply problem. In the industry, we see a huge shortage of talents who can excel in both system design as well as algorithm design. And that's the main challenge we try to target in the industry today. To further complicate the story, as this work shows, which has been presented in DAC Conference 2021, it's not just the robot itself. We are not limited to only on-vehicle computing, but some new compute paradigms such as infrastructure vehicle cooperative, autonomous driving, or cooperative robotics, and so on and so forth. Different robots and different autonomous machines talk to each other, communicate and share their perception results, for example, that will further complicate the pipeline. And it's even more increasingly challenging to design systems for these kind of scenarios. So what's the wish list from the industry? The wish list is as follows. You see there are many different kind of applications, whether it's a drone, it's an autonomous machine, autonomous vehicle, autonomous robot, or delivery robot, and so on. If we were hiring high-level programmers, application programmers, we want the application programmers to be able to focus on only the high-level programming, such that the high-level programming language will combine the basic operators, whether it's localization, whether it's planning control, and so on, to form a computation graph such that their applications can be implemented. But that demands a lot of work at the basic operator level, at the runtime level, and the compute substrate level. Especially, we design programming language on top of a defined architecture. So what's the computer architecture for robots, for autonomous machines, still being defined at the moment? We see three trends of computer architecture abstractions. First, it's a data flow or data flow-like architecture. That's very natural fit for autonomous machine computing. As we have shown in the first graph, naturally, these autonomous machines, they form a data flow graph for computing. So a data flow accelerator architecture, let's put it that way, would be a natural fit for robotic computing, such that we have different accelerators for different kind of functions, whether it's localization, planning control, and so on. But the drawback of that approach is that, of course, you have to define a lot of accelerators and integrate a lot of accelerators onto the same chip. That could take a lot of chip space, and you need a lot of volume to sustain that growth model. The second model, which we focus today, is a vector graph architecture. Remember, we talked about that there are many different blocks. You may need many different accelerators, one for each block. But we have discovered that many of the blocks can be represented as a vector graph architecture. So if we can accelerate vector graph, that could be a natural solution to the architecture definition. So that's what we are going to focus today. And then we will use one example, LiDAR-Inertial Odometry, or LEO, to explain the vector graph architecture. Then, of course, you see a trend of end-to-end deep learning architecture, such that you use a transformer at the front end to combine different sensors to give you a overall road representation. And then in the back end, you can use different deep learning models to compute. And that's still under development. But for today's talk, we'll focus on vector graph architecture. So what is vector graph? I think the best way to start is to read this book, Vector Graphs for Robotic or Robot Perception, to explain what's the application of vector graph in autonomous machine computing. It's fair to mention that vector graph can be successfully applied to a lot of functions, including localization, planning, tracking, control, and many more. So it could be a very good candidate of a common abstraction, a common accelerator block for many different robotic functions. Basically, it can be used for state estimation. It's an optimization method for state optimization estimation problem. And many of these basic blocks are actually modeled as a state estimation problem. That's why vector graph could be a natural fit for autonomous machine computing. So what exactly is a vector graph? It's a bipartite graph, such that there are variables that represent the state that you are trying to estimate, whether it's a trajectory you are going to generate, or it's a robot position and heading that you try to estimate. The factors are more or less the observations and probabilistic relations between different states. For example, a joint probability distribution can be factored as the following vector graph, and can be computed using the following equation. And that's a high-level representation of vector graph, just a representation of how you compute or how you represent a robotic computing or autonomous machine computing process. There are three steps. We're going to talk about vector graph architecture or vector graph computing in general. There are three basic steps. First step is you have to use the abstraction to represent your computing as a vector graph. And then the vector graph mathematical operation would allow you to do some optimization within such that if you have a sparse matrix, you can generate through optimization, mathematical manipulation, to generate a more dense matrix for you to compute, and it's easier to compute. And I believe a lot of the sparse matrix computation would take up a lot of memory, and the decomposition process can take up a lot of computation time as well. And Photograph is here as a unified model representing various forms of these optimization problems, and then facilitate better sparse matrix data storage and so on. And then also they have mathematical operations to improve the efficiency of matrix decomposition. That's why we think Photograph is a beautiful, beautiful representation of autonomous machine computing. Oh, by the way, sorry about that. So step one is you need to represent your computing as a photograph abstraction. Then you perform mathematical operation to do optimization. Then last step is to move it to hardware to do acceleration. So we follow these three generic steps to achieve better photograph computing results. So there are several traits of a photograph. For example, variable elimination, that's a very nice trait to have. On the very left side, you see original photograph, but through operations, you figure that some of the variables can be eliminated. So through a few manipulation steps, you can eliminate a lot of variables through the process, through pure mathematical operations. Then at the end, you get a fairly dense upper right side matrix that's much easier to compute compared to a very sparse matrix. And it's storage friendly as well when you do that operation. So that's first trait. So once the first trait, in short, is once you represent something as a photograph, there are a lot of operations you can utilize to optimize the whole computation process. Second one is unique to LiDAR-Inertial Odometry. When we represent it as a photograph computing process, it can be featured as a chain-like architecture. It's quite symmetric. So that would give you a lot of opportunities for optimization, as we will discuss later. So what are the algorithm level optimization? There's two fundamental operations in photograph computing. One is variable elimination, and the second one is backward substitution. So when we design a accelerator for that, these are the main computation that we have to use. Because for LEO, LiDAR-Inertial Odometry, it's a chain. So you can avoid a lot of vector searching process because you just traverse through the chain. And that would give you a lot of opportunities for optimization as well, as we will discuss in detail in the paper. So if you are interested in these optimization techniques, we will not cover them in detail due to time limit here, but welcome to check out the paper for more details. Besides that, it's easy to traverse through a chain compared to traversing a graph or more complex data structure. It gives you opportunity to parallelize the whole optimization process, including the elimination process and the back substitution process. Here we show some tricks how you can do parallel elimination and parallel back substitution. That would give you a lot of opportunities for block time multiplexing, and as well as computation speed up and optimization. So after discussing the basic idea of photography and optimization opportunities for photograph, now let's jump into the accelerator design so that you see what we can implement in the photograph domain, such that we can apply these techniques to not just the LEO, the LiDAR-Inertial Odometry application, but many, many more applications to come. Basically, here's the high-level architecture for the LEO application, such that you have input buffer to buffer the LiDAR signal, the IMU, and so on. Then you have a block called sensor factor. The sensor factor, as we can see, there are a lot of ways for you to do circuit sharing to optimize the utilization of hardware real estate. And then you need a linear system buffer. That's for storage optimization, because photograph, the original or raw representation is quite sparse. It could take up a lot of storage space, but through linear buffer, we can optimize that. Then at the back end of it, you have a partial QR decomposition block, which is the computation pipeline for pipelining and parallelization to optimizing traditional optimization techniques that can be applied on top of it. First of all, it's a circuit sharing. It's for computing the Jacobian matrix and residual optimization and so on. So a lot of computation results due to the structure of vector graph can be reused. So if you buffer those computation results, you don't have to recompute. That allows you a lot of opportunity for optimization. Also, the function units in the sensor vector block can be optimized through time multiplexing as well. So that's the first optimization we have applied to the vector graph or accelerator design. The second thing is storage. Storage, especially on an FPGA or even ASIC, storage, it's very limited precious resources. You have several optimization techniques that we can apply here as well. Option one is we use a sparse vector graph structure. We compressed it such that it fits into a limited storage. Second is that we can utilize the chain-like property that's unique to a Leo application, such that we can bring in new blocks like in the pipeline fashion. So, in this way, we can streamline the whole process and fully utilize the storage source. The third one, it's fine grain. We can utilize the property of fine grain sparsity in factors. We can skip all the zeros and identical matrix at fixed positions so that gives us additional opportunity of eliminating storage needs. Through these three options, we can further optimize the whole storage system for Leo. Then we talk about QR decomposition. The QR decomposition can be evaluated in a pipeline fashion so that the hardware, it's like a traditional 5-stage pipeline process we use in RISC architecture. It's the same logic, such that you read in a line, update, then once you finish that, you push it into FIFO, then the second update will fetch from the FIFO compute. So we not only parallelize the whole process, we can pipeline the whole process. So we have multiple, regarding parallelization, we have multiple update units, so we can work simultaneously. And this update unit, they naturally form a pipeline of computing such that everything that goes into the system can streamline through it. That's how we design our QR decomposition block, hardware block. So we have discussed multiple optimizations, specially tailored for vector graph computing, whether it's QR decomposition or the storage design or the time sharing of the Jacobian matrix computation circuit. What are the results, right? The next big question is, if we were to make this into an ASIC or accelerator chip, what are the results? So here's the baseline we use. The hardware platform is a Xilinx Zinc 7000 series SoC. We picked two very public data sets regarding LiDAR-Inertial Odometry. One is the PARC data set. You can see we put it down here as reference. The second one is the walking data set. The baseline is a GTSAM, which is a software solver that we run it on a Intel processor. Then we also run the same GTSAM on an ARM Cortex A57 processor. And let's look at the results. Regarding speed up, it's quite amazing. We have achieved 9x speed up compared to the Intel baseline, almost 50x speed up over the ARM baseline. Regarding energy efficiency, it's 50x more efficient compared to the Intel baseline and 17 times more efficient compared to the ARM baseline. That shows us, that gives us a very high confidence and confirmation that accelerating vector graph, it's a very good technique as a general accelerator for not just the Leo applications, but a lot of the robotic applications in general. Another question many may raise is, what are the accuracy? Did you sacrifice any accuracy in order to achieve that? No, we don't see any degradation of accuracy. And then for particular techniques that we have applied, we actually gain further resource saving through this minor optimization on top. So the conclusion is that using this technique, we not only achieve a high energy efficiency, high performance improvement, we did not sacrifice any accuracy for localization, because after all, that may be the most important issue. especially a lot of the robotic applications, they have huge or very high, very strict real-time demands. I think having a accelerator to satisfy a general accelerator to satisfy different demands, it's a very good approach, especially from the computer architect perspective. So conclusion, it's the first piece of work to use hardware accelerator to explore vector graph architecture for autonomous machine computing. And we start with the LEO, which is a key application, localization application in a lot of different robots, whether it's a autonomous vehicle, or mobile robot, and so on and so forth. LiDAR-Inertial Odometry is a key block for localization. And through this first initial work, we leveraged data and computation patterns inherent to the vector graph computing and inherent to the LEO application to optimize the whole hardware architecture. We achieved significant acceleration results and energy efficiency results. That actually gave a lot of encouragement to us to continue the work to apply vector graph computing to many other applications in robotics as well. So the next piece we will focus on planning, which is a very important piece of work or application in robotics as well. Also, we will apply it to tracking. Once we finish these different pieces of work, we can consolidate and develop an architecture, vector graph computing architecture for autonomous machine computings. So that's the end of my talk, and thank you so much. And really enjoy sharing the latest industry insight with you guys. Now it's time for Q&A. May you have any questions, just let me know or shoot me an email later on. And thank you so much.